All right, hello folks. Another review slide coming up, and I need to change the organization on my PowerPoints. There we go. Pen color. Let's go with blue. So today we're going to review how to balance reactions. So when we're looking at reactions, we've got several definitions that we need to know, and these are things that are attached to the reagents and products or reactants. So let's start with reactants. Reactants are the same thing as reagents. They both mean the same thing as stuff that we start with, or stuff, and they're going to be on the left-hand side of the arrow. And products is what we end with. That's what we make. And so these two are the easiest, and what people get a little mixed up about it are these 5 things. This is a solid, means this. And sometimes you may see an arrow pointing down, meaning precipitates. Or a solid is made. So you have S as a solid, and then L is a liquid, B is a gas, G is a gas. This is aqueous, meaning that the compound is in a water solution. Now, so we have this water solution, and that's what aqueous means. And then this means heat, which changes the temperature, and usually we add it by adding heat. And you're going to see this in all our equations, especially on the owls. And now remember, the reagents are always on the left, and here's our arrow. Sometimes it's also expressed as this. This means equilibrium, arrows going back and forth. And the products are made on the right. Underneath, above or below the arrow, you're going to have reactions conditions that tell you what's going on. It may be solvents that the reagents are in. If it's not water, catalysts, we add temperature. Sometimes we see the heat up here. Inhibitors, pressure of the atmosphere, because pressure can affect reactions, and any other important information that we may know to help us do this reaction. So this is what we have as an equation, and sometimes they're not balanced. And so to balance these equations, we've got to conserve mass. Conservation of mass is something that Dalton had. And so for any chemical reaction, the number of atoms on the left-hand side must equal the number of atoms on the right. If we produce a gas, it has to be included in the equation, because it doesn't, it's there, even though it goes away, it comes out of solution, but we still have to treat it as being there. And so a lot of times, we write a chemical equation, and you get this a lot in college. Butane gas plus oxygen gas produces carbon dioxide gas plus water vapor. So everything is a gas. Gas, 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 water vapor. Gas, 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 vapor. Well, that's a gas. G. So butane is this compound here, C4H10. Oxygen gas, carbon dioxide, and water. And this is a combustion. Now we have to balance it. So we're going to come back to this one, and we're going to talk about balancing. Next, you got to identify and count the number of atoms on each side of the arrow. Then, starting with the heaviest element, leaving oxygen and hydrogen to last. And you got to change the coefficient in front of the molecule in order to balance the equation. And when you do, remember, if you add a molecule, all the elements in the molecule must change. And sometimes you're going to end up with a fraction. And there's a couple ways to deal with this. I like just make one of them a fraction and then multiply by 2 to get rid of everything. Get rid of the fraction. Excuse me, it's been a long day today. So I'm going to show you how that works with the next example. So here we are. Butane plus oxygen gives me carbon dioxide and oxygen. So what I like to do is go CHO. All right, in the middle. On the left-hand side, we got 4 carbons, 10 hydrogens, and 2 oxygens. We got 2 here. Now, on the left-hand side, now remember, oxygen is in both molecules. Carbon, we just have 1. Hydrogen, we just have 2. And oxygen, we have 3. Now, so in order to balance this, we take the heaviest first. Hydrogen and oxygen always last, mainly because either oxygen can exist as O2 gas as a product, or hydrogen is usually H2 gas as a reagent, as a product, and O2 is a reagent. So this is why we leave these two last. So let's go ahead and balance carbon. 4 on the left, 1 on the right. We want a total of 4 or 3 more carbons. To do that, we have to add 3 more CO2s to this because 1's implied. So change this to a 4. This becomes 4. Now carbon balance. 2 times 4 is 8 plus 1 for 9. This is important. You've got to make sure you change both carbon and oxygen because you're adding molecules of CO2. CO2 cannot break up. When you're balancing equations, you got to treat the CO2 as one entity. If you're adding 3 more for a total of 4, you got to add 3. You got to add the appropriate number of atoms of each element. Now, which one's next? Is it hydrogen or oxygen? This is where you look at this carefully and say, okay, I have O2 by itself, because if you have O2 by itself or H2, whatever oxygen and hydrogen is by itself as a diatomic gas, that is last. So hydrogen is next. All right, so I've got 10 hydrogens over here. Hydrogen shows up here in water. We need a total of 10. So since there's 2 hydrogens in each molecule, I need a total number of 5 or 4 more in order to change this to balance the hydrogens. Now we need to balance the oxygens and add them all up. So here we have 8, here we have 5, and if we add those together, we're going to end up with 13 total. So 2 times 4 is 8, plus 5 gives me 13. So we've got 13 oxygens, and we've got 2 over here. Now this is where, if you do this right, it makes all the sense. So everything is balanced but the oxygen. If I go 13 halves of O2, I'll end up with 13 atoms of oxygen. Now if I do it this way, 13 over 2 molecules of O2, and for every 2 atoms for every molecule, 2 cancel, and we end up with 13 atoms. Nature really hates fractions because you don't have a half oxygen. So we end up with, I'm running out of space. Let me get my eraser and let me erase all this. Come with a pen. All right. So this is now 13 halves. So we have C4H10 plus 13 halves O2 goes to 4 CO2 and 5 H2O. Now, since nature hates fractions, we got this fraction here, multiplied the whole equation by 2. Everything will still be balanced. But now we don't have this fraction in front of the oxygen. And now we have the balance equation. This is how you balance these equations. This is what I want you to do on the practice in AL and for the exam that we're going to come later. Now, we're going to do this one. Balance the following equation. Now, I want to point out that NO3, nitrate stays together for the most part. So we're gonna do a little trick. Ag, this is the equation we got to balance. HS, I'm going to keep NO3 as a group, mainly because it doesn't break apart. So we have one silver, two hydrogens, one sulfur, and one group of NO3. On the right, we got two silvers, one hydrogen, one sulfur, and one group of NO3. See, this does not break up. So let's go ahead and do the heaviest first. That's going to be silver. So we need to balance the silver out. We need a total of 2 in front of the Ag silver nitrate. We have 1 already. Now we need 2. So this becomes 2. And now we have 2 groups of NO3. All right. Sulfur is balanced. Don't have to worry about that. Now we need to worry about nitrate. We have 2 nitrates on the left. We need 2 on the right. Total of 2. So to do that, we change the number in front of here to a 2. Now we have 2 NO3 minuses, and we add additional hydrogen to the right. And voila, now we have it balanced. So the balance equation is 2 molecules of silver nitrate, AgNO3, plus 1 molecule of H2S gives me a molecule of AgS2, Ag2S, and then 2 molecules of nitric acid. So in other words, we have 2 moles of silver nitrate plus 1 mole of hydrogen sulfide gas reacts to produce 1 mole of silver sulfide plus 2 moles of nitric acid. And that's how we balance this reaction. This is the end of the lecture, guys. Have a nice day.